Hello, welcome to this one. In this one we're going to go over the trampoline hooks. A trampoline hook is a pretty common type of function hook that you're going to use in game hacking or any sort of, not just hacking use cases, there's real world use cases as well. For instance, API hooking, things like that, if you want to see when things are called. It's also utilised in security as well. So obviously two sides to everything. So a hacker will use function hooking to potentially redirect execution flow, whereas you'd hook a function to detect what else is hooking it, things like that, or you'd monitor hooks for function, you'd monitor what function is being called, those kind of things. Anti-cheats will use it, EDRs, all those kind of things. But in this video we're going to focus on the trampoline hooks. We're going to discuss a little bit about hooking, but primarily what the trampoline hook is and how we can implement it both in x86 and x64. So right away, for people uninitiated, what is hooking? So hooking is altering the behaviour and flow of execution of a typical software. It's not just referring to applications, it can be an OS level, any sort of software. Hooking can just be redirecting that sort of flow of execution, modifying parameters, things like that. In our case, function hooking typically redirects the execution flow to a custom function and then back to the original function, and this is known as trampolining. Obviously trampoline going up, down and back, things like that. That's why hence why it gets its name. And there are many ways to hook functions. We're not going to discuss technically we're going to discuss two in this video, being the basic jump hook and then obviously a trampoline hook, which is building off that. But there are many ways to do that. I'm going to leave a brilliant article by Julian Bremer in the description. A fantastic security researcher, and this article was made a very long time ago now. I believe it's 2012, but it's still ever so relevant today, and that is where I learned a lot of what I know in terms of function hooking from that and what I've built upon from that, and I highly recommend you go and read it. It is absolutely fantastic. So starting off with trampoline hooks, so a very simple diagram, nothing too complex there, but basically all we're gonna do, the original function that we want to hook, we're gonna place a hook and we're going to go to our custom function, and then from our custom function we're going to then jump back to the original function here. In this sort of portion here, in our way back to the original function, this is going to come from the form of a code cave. So we're going to basically have three jumps, one from the original function, one from our custom function to a code cave in here. The code cave is then going to jump back to the original function there. All a code cave is just a portion in a process that's sort of got memory allocated to it for, as it sounds, code or just sort of bytes, things like that. In reality, a code cave can sort of be any sort of memory in a process, but in this case, when I'm referring to code cave, I'm basically referring to the stolen bytes and where they're going to be placed, which we're going to talk more about in a minute. So finally, trampolines explained. The original function has some sort of hook placed, and this is typically a jump instruction. So at its most basic primitive level, a trampoline hook or any sort of function hook, we're just going to put a jump right away there. It's the most basic way of doing it, nice and easy. The jump instruction then redirects flow to our custom function. Obviously, the whole point of relative jump, it just jumps the address you specify. And then our custom function jumps to a code cave, which contains the bytes we have previously overwritten in the original function. So these bytes that we then replace with our jump instruction, these are known as stolen bytes. After these original stolen bytes, we have a jump back to the original function, this time jumping to a location after our hook is inserted to avoid an endless loop. So if you think about this diagram back here, when we're jumping from our custom function, when we're going back from our code cave back to our custom function, if we just jump straight back to the start of that function, we're going to hit another jump and it's just going to go in this loop all over again. So what we need to do is we need to account for that, and we need to do a slight calculation and basically just go after that jump instruction. It's nothing difficult, it's quite literally just the space that we've allocated our jump instruction and potentially some padding, and we're just going to jump after that. So just to reiterate again, when we insert a jump instruction in an original function, or when we're going to redirect flow, we always want to take those stolen bytes so we don't corrupt the stack, and so the original function still executes correctly. And these are in the form of stolen bytes. So we're basically going to copy these bytes to a buffer, and then we're going to put them in a code cave. So they're executed, and then when the jump's executed, it's going to go back to the original function as if nothing's ever happened. It's just going to get executed as normal, and the stack remains the same. It's not corrupted. So implementing trampolines via C++, as we've just talked about, this is a pretty simple rundown of it, and it's not very complex, but it can get a little bit confusing if you're not familiar with it. But we're going to go through it slow time, both in x86 and x64, so don't worry, this is just a very simple, primitive way of explaining it before we start. So we will start by writing a jump instruction, our original function, to the hooking function. So all this is going to do is just going to jump from the original function to a hooking function that shows in that diagram here. This is just this part here, that's all it is. And then after, we'll allocate some free space inside the module, and this will be our code cave. So basically, there's a few ways you can do this, but it's not a very complicated example. So all we're going to do is we're going to allocate some space rather than try and find some free memory. We're just going to use virtual arc, something like that, to create some space for our stolen bytes and the jump instruction. Code cave there. We're going to store the stolen bytes there, and we'll copy that we copy from the original function, as well as our jump back to the original function there. As I said before, that jump is going to go after the jump in the original function, so it's not an endless loop. And potentially we're going to look at unhooking as well. Very simple, just patching it out. We're literally just going to replace the stolen bytes back, and then potentially there's a few different ways we can go about doing it. We can either remove the code cave completely, or we can just sort of just leave it in process memory in case you want to rehook later. It depends how you want to do it. Right, so we are in Visual Studio, and we're just going to be going through the basic sort of implementation of a trampoline. First in x86, and the first sort of thing we're going to look at is just an inline jump. So we're just going to be placing a jump instruction, and we're going to basically redirecting code that way. We're going to do it just all in this module here. We're not going to be injecting in our own DLL, but the process is the exact same. If you wanted to do it so you go into another module, as in real world, you just take the code that we're going to write here and just put it into a DLL, and then obviously just your method of choice inject into a process that way. I've also left a little link for references for shellcode if you're interested. This is just one pretty decent, like fairly human readable one for it compared to a few others. If you look at, they're a bit harder to read, but this one's nice and easily laid out for you. You can see why that's relevant in a minute. Right away, we're just going to go and just going to create some like test functions and just what we're going to need. There we go. There we go. So all we're going to use these functions for is just basically to demonstrate that we're gonna hook this basically. And as I've said, we're gonna do it just in the module itself, but the process will remain the same. So 1 second, we'll create a loop as well, just so we can see that it is actually we've actually hooked the function. Key state. And then we'll just call this function whenever we press escape. Get rid of this, don't need that. Happy days. Should absolutely kill our processor. There we go. So all we're going to do here when we run this, again, make sure we're compiling x86. We'll cover x64 in a bit, but for now, we will. There we go. So when we press escape, there's our test function executing there, as you can see. And for the minute, that's all we want. Happy with that. So now what we're going to do after this bit of code here is we're going to write some code that will basically hook this this function here. So we will get right into it. So there we go. We will we'll just call it place jump. So we'll take a destination or source and destination. Get size as well. Talk about a little bit what we're going to do. We're going to basically take our source, so where we want to go, where we're going to go, place a hook, destination, where the hook's going to go to, and the size of the hook we're going to be placing. So we're going to talk a little bit about what we're going to do here. So placing a jump instruction. In fact, right away we will just there we go. We'll just put some stuff down. It's a little bit easier. There we go. And we will. So we're just going to print out a few things that just makes it a little bit easier for us to see. So we'll just run this quick and we'll open it. No, we can't open it. 1 second. There we go. We'll open it up in a debugger. and we will go to this address here. Happy days. So as you can see, this is our function. Oh, I've gone to the wrong one. Nice one. There we go. This is our function here. So as you can see, test function. This is it right here. Now, if you look, this is just a default function. Prolog here, we'll just set default function setup, setting up the stack. Then obviously the function's doing its thing here. Pay attention to the sort of the start of the function prolog here, and what we're going to need to do. So the minimum sort of space we need to actually place a jump instruction is 5 bytes. Reason being, a jump is 5 bytes in length. So 1 byte is the opcode, and then the 4 bytes are the relative address that we want to go to, or the address we're going to go to. And the reason why I say relative address is because the address that this jump is going to go to is going to be a calculation. It's not going to be a fixed and absolute address. We will do some calculations in a second, going over that. So all we're going to do now is we are just going to, firstly, we're just going to make sure that we have access this memory region. So the word, oh, there we go. Never remember what's what in here. So we'll take our source, want the size, what is this page? Let's keep reading right. There we go, and here we go. So all we're doing here is we're basically saying from our function, this portion of memory, the memory that we're going to be touching, we want execute, read and write permissions as well, so we can read, write and execute. We can specify others as well, but just for this example and just ease of use, we're just going to have everything that we need, or just everything there, just to avoid errors basically. We'll copy this as well, so when we're finished we can just restore the old protections there as well. If we don't do this, we'll get an access violation, because we will obviously not have access to that portion of memory. Even if we're inside the module, we always need to do this, otherwise it's just going to give us an access violation. So once we've done that, well, then we're going to dereference our function pointer, and then we're just going to basically say, in fact, no, we're not. We're going to first copy. Oh, no, we won't. We'll save that. We're just going to sit for the minute. We're just going to quite literally just place a jump. So all we're saying now is at the start of the function, we're just going to place a jump instruction. So this is dereferencing the function location and the area in memory. This sort of function prolog here, we're basically going to say at this instruction we're going to overwrite this with a jump. So the opcode for a jump is 0x e9 in hex. So that's placing a jump at our destination address. Placing a jump at source func. And then we need the relative address. Now, if you want an in-depth explanation of this, go read the article I've linked in the description from Julian Bremer, as I've already mentioned. Highly rate it. It's an old article, but it's so very much relevant today. A fantastic reverse engineer and malware analyst, and he's where I sort of learn all my sort of things about hooking from. It's a really good article. But all we're going to do is we're going to calculate a relative address, and this is just the location. Oh, sorry, from the source location to the destination location. The reason why we have to do this is because the instruction pointers are going to change, and it's going to just take up some more space. And if we don't do this, it can take us to the wrong location essentially. So we want to go from function B. How it will go is dest. So this is the calculation that we want to actually do. So dest minus source minus 5. So 5 is for the instructions that are our relative jump, and then our destination at minus in our source address there. So this would be just this here, dest minus source, and then minus 5, obviously for our full jump instruction. If we didn't do that, we would just be placed incorrectly. We'd either be in front or behind of our jump, that kind of thing. Obviously we need to take into account the size of our jump there. So with this address, we're then just going to go one more, so +1, and then we're going to write the relative address to that location there. 1 second. There we go. All going well. From this, we should now see jump to our destination function here, and we'll just create another function here. Call it hook_func, printf, and we'll just call it hooked. And for now, all this is going to do is just overwrite the function. This is not a trampoline. Apologies about that, I've just had a phone call. Whilst on the call, I've just made a few key changes to our code here, and I'm just going to go over them now. So, main one being here, the one that actually causes great issues is just this type change here. We've just casted this, instead of just dereferencing the pointer, we're just going to cast it to a uint pointer t. Or uint pointer type, sorry. Reason being, through my debugging, when I previously wrote some of this code, I had a lot of issues with types. C++ is a type-safe language, so if you use the incorrect type, you are going to know about it. And if you are having problems, so if you're writing your own version of this, you think I'm going to try different types, like things like that, have a look in the debugger and just see how it impacts. Have a read on what the types actually are. And in my case, sort of most of the time, I get the best results with the int pointer type here. Both in x86 and x64, because this type here it's a good type to use, because it will sort of automatically just convert on both systems for you. So there's certain types that are obviously going to be hard coded. For example, D words or Q words are going to be x64, x86, but this will transition the same with char pointers. It'll also transition based on the architecture you are on. The compiler will automatically detect that obviously a char pointer on x64 is 8 bytes, and same with the int pointer on here as well. It's going to be 8 bytes on x64 and 4 bytes on x86, so that's why I like to use it. It's sort of architecture agnostic, if you will. It's not going to bother if it's x86 or x64. It'll work on both, providing obviously other code does as well. The only other change I've done here as well, which we'll talk about in a second, is I've just quickly added this here to basically pad the function. Now, what this means is if, let's say, we need at least 5 bytes in our function to hook it. If we cannot get sort of a matching set of instructions that fit into that 5 bytes, if it's less than 5 bytes, we can't hook it. But if, let's say, we have 10 bytes, so our instructions sort of fall over and they don't equally fit inside those instructions, we're going to need to sort of pad it with nops. Otherwise, it's going to give us some issues and it's going to error out. So we will just go to our function. I'll explain what I mean. So if we go here, as you can see, if we look on the left here, for our bytes, we have 1 byte for that instruction, and then we get total into 3 here, and then we have 9. So what that means is 5 bytes isn't going to fit, let's say, into these instructions here nice and like easily. It's going to have 4 bytes left over. So basically, we need to sort of fill them. We need to fill that excess space, and the way we're going to achieve that is by padding it with nops. Now, if you're unfamiliar with a nop, it just stands for no operation. It doesn't do anything. It's defined. So instruction that does nothing. It is a standardized instruction, so it does exist as nop. That's its purpose. That's its sole reason for existing. Its whole point being there is to do nothing. It's recognized by the processor, and it is just essentially ignored. It's just obviously the processor still goes through and detects it as a valid instruction, but it just doesn't do anything with it. It knows not to do anything with it. So that's why we are gonna use it. Happy days. So I think that is everything for us, and if we place this jump with any luck, we should have a nice hook. So we will go from our test function here, and we'll go to our hooking function. Oh, I've missed it. Hooking function, and then we want 9 bytes, as we've just seen there in our debugger, the amount of space that we need. Jump pointer there. Pointer as well. Done like that. So with any error, with any luck, we will have placed a jump. Happy days, as you can see. And now if we open this up in the debugger, we'll have a quick look at it. So as expected, what's happened here? If we go to our function, obviously the hook has been placed. It is going to our hooking function, but it's not quite working as intended. We're going to talk about that now. So if we go to our original function, as you can see that these bytes haven't been overwritten. Reason for that is this address that we're getting here when we sort of get the address of our function. This is going to our jump or link table basically. So this is just the jump table, the list of jumps in our module essentially. So what we're saying is dereferencing that pointer, we're going to go to this address, and then obviously as it's doing here, it's overwriting the first instruction with a jump, and it's just adding a little nops here, so it's doing essentially nothing. But it's not dereferencing our original function correctly. So we need to obviously remedy that, and we're going to do that by just directly going to the function here using a relative address. So we'll go back. This is how you'll do it as well if you're doing it in a module, things like that. So it's a bit more better example. So we will want to get our module base address. Base equals get module handle A. In case you didn't know, if we just put null in there, it'll just get our module base for the module we're currently calling this in. Happy days. And then with that, if we just replace this, we should module base plus the relative location of our function. With any luck, we should have it functioning correctly. Happy days, that looks a lot better. It's not giving us an error, so that is a good sign. Now if we go back to our function, it should work a little bit better. There we go. This is what I was talking about before. As you can see, straight up to the 8th byte here, it's just padded it with nops. So happy days, there is our jump and our relative address taking up 5 bytes here, 1, 2, 3, 4, and then to the 9th byte, our next instruction, setting up the stack here. All correct, all working, and as you can see, we're just going to our hooking function here, and this is the prerequisite, the sort of the basics that we need to get our trampoline set up. And right now we're just going to go back and sort of go on to the next step of how to set up our trampoline. Right, so before we begin talking about the next sort of step of our trampoline, we're just going to quickly discuss something to sort of explain how we're going to set up a trampoline. So just after this, I'm going to be showing you sort of a more visual example of how the trampoline setup actually works, but this is sort of the latter end of the trampoline. So basically, we're going to set a jump instruction to our hooking function, so that just essentially overwrites the original function. It's not going back to the original function, and then in this next part, we need to then take it back from our custom function to the original function. So we're then going to jump from our hooking function here to a code cave, which is just a dynamically bit of allocated memory. Inside that code cave, we're going to have some stolen bytes, and in those stolen bytes, we're then going to have another jump back to the original function. Now, the way we actually achieve this jump from our hooking function to the code cave is actually through function pointers and prototypes. So I'm just going to give you a little example and just show you what I mean right here. So normally when just a typical function setup is going to be, if I put a breakpoint in the function, as you can see, test function 2 here, nothing special, and we're going to have a look, see exactly what's happening with this function here. And as you can see, the first address on the stack is going to be the return address to where the function was called. So if you remember that value, it's 6D80. We're going to go and we're going to find main, and we're just going to find that address there. So let's look for 6D80. There we go. Right, so this is the call to our function. So if we follow this, this will go to our function. As you can see, the return address there after the function has been executed, one instruction after, there we go. So here we go, test function 2. Right, so if we just step through this function, we'll see when it function returns, all a return instruction basically is a jump to an address, basically just a place in memory, place in the module. Same with the call instruction. The call instruction is a little bit different, but they both essentially do the same thing. They will just jump to an address. So if we just step through this, as you can see, it's creating a stack frame, doing its thing. Once we get to the bottom and the stack's finally cleared, as you can see there, it's gonna in the stack back here, stack frame down here, it's gonna jump back to this address here. So if we just go through, there we go, and we've gone straight back to our address. Now, if we go back in here, when we're gonna call our custom function here, we're going to change some things. Instead of just returning its typical value, because it's not going to return, it's only going to basically execute in our module, but what we want to do is actually return it back to our code cave, or the pointer of our code cave, I should say. So to achieve that, we're going to use function pointers in C++, which I'm going to go over now. So all I've done is just define a type up here, and then we're just going to assign a value to this type. As you can see at the minute, this function pointer is just a null pointer, so it is going to give us an access violation, but this is perfect for learning. You're going to see how it differs from the code that we've just looked at. So if we recompile this, the code is going to look a little bit different. So the compiler is going to change how this works. Instead of just going through the process and returning back to its original location, it's actually going to make a function call. Let's get this open and have a look. Happy days. So if we, there we go, make our call, and we'll step through this, and you can see it straight away where it's going to make this call. As you can see here, this is where this function pointer, it's returning. So it's basically, you think it's just going to, or it's going to be the end of the function, it's going to jump. But in actual fact, what the compiler's done is it's done this instead. It's created a new function call for us, so it still fixes the stack. And this is sort of how we're going to do it. So if we just step over this now, it's going to give us an access violation, because that's obviously not valid memory, as you can see down the bottom left. So this is how we're going to achieve basically jump into our code case. Because if you think about it, if we had our hooking function here and we were to try and add a jump instruction at the end of this, like this, return an address there, if we just wanted to add that at the end of our function, that's not how it works. We can't just do that. It wouldn't work. It would error out. Reason being, we can't just add random bytes to a function in extra space. So how we get around that is instead we just return a function pointer and then we call it, as you can see through the code here. And then once that's called, that'll take us to our code cave, and then once we're inside the code cave, it can execute our stolen bytes and just jump to the original function, nice and easy. So what I've just been discussing with our function, returning a function pointer, this is essentially a more in-depth diagram of what we're actually going to do with the trampoline. So we have the original function, which is then going to have a jump inserted that's going to go to our hooking function. That's just what we've done now. We've inserted our jump, and that's a basic hook, and all it's going to do is just do this. But with the trampoline, it goes all the way around and it goes back to the original function. Now, where things get a little bit more complicated is going from our custom function back to the original function. So from our custom function, we need to have a jump going to a code cave containing the stolen bytes, which also contains a jump back to the original function. That's really easy. That's essentially the same as just writing a jump to our custom function, and all we're going to do is just put some bytes in front of it. Dead easy, just allocating memory. This can be a little bit more complicated depending on how you want to do it. And the way we're going to do it is just, as I say, we're going to use function pointers and just return the function prototype that's going to go to that pointer, instead of also having to do some other tricky way. Obviously we can't add bytes to the end of our function, as we've already discussed. That's just not how it works. So to get around that, we're going to use the return instruction, which is going to jump to our code cave. As you can see, it's not quite how it works. When we look at the disassembly, it doesn't just go straight from a return and jump to it. It actually creates its own call. Depending on the compiler, things might be a little bit different, but that's just one nice easy way of doing it for us, and that's how we're going to do it. Okay, so now we're going to go on to the next stage of our trampoline process that I've just explained. We're going to go on to the code portion of that. We're going to have to make a quick change to this function here. So initially, when I was going through this function, obviously we didn't do this, but now we're just going to add an extra parameter, and it's just going to be some stolen bytes. So basically, with these stolen bytes, we're going to place these into a code cave, and then we are going to execute the stolen bytes when we return to the original function. So right before we start overwriting anything, we will just copy all of these source. We want it from the source, and then we want it from the size that we're going to be overwriting. There we go. Oh no, sorry, my bad. The source and the size there. Happy days. So this is basically copying our stolen bytes. So all we're doing here now, when we create our trampoline, we're going to be using our place jump functions. This is going to just basically add in jump instructions to the start of the function for us, going to our new function, which is great. And then all we're going to do afterwards is just set up our function prototype and insert a trampoline that way, and this way we can achieve all that once we've got our stolen bytes here, which is great. So now we will start working on our trampoline function. So the parameters are going to be the same essentially, so we're just going to need a source and a destination, and then we'll obviously need a hook size as well for our jump function. There we go. What we've done here, bosh. Right, so right away, once we've got everything set up, we're basically going to create a new buffer for stolen bytes, and this is just going to be the bytes that we're copying over from our original function. Byte, oh, my mistake. There we go, and then we're just going to specify that to be the size of the hook. So all this is doing here is just creating a dynamic buffer based on the size of the hook that we're placing, and this will be where the bytes that we write to our code cave. So all we're going to do now is just place our jump. I'm going to need the source, the destination, the size, and we will want the stolen bytes. And that went like that. There we go. Happy days. Great one. So now we're going to create our code cave. So trampoline code cave. I'm just going to use virtual to do this. This is going to allocate some memory in our process. There's a few different ways you can go about doing this. So we obviously, I'm showing the most simplest way possible. We'll think about this from a perspective as well. We could find pages in memory that aren't used, or just regions of the process and the module that haven't been used. We could go into other modules as well that exist within the process and do some things there. All sort of things just to be considerate of. But in our case, we're not going to want a specific address, so we're just going to leave it as null. The size that we're going to want, so there's a few ways we can sort of go about this. We can either do it as in the exact size we need, which we calculate that if we wanted to, as in the size of our stolen bytes for our jump instruction, which is going to be roughly however many the size, then +5. So we could do that if you wanted. Just for this example, I'm just going to use a static 100 bytes, but again, that's just another consideration, improvement to potentially make, just to be considerate of. I say if you want that to be dynamic, we could just do size plus the size of a jump instruction, and then we're just going to set our sort of page permissions. So and then reserve, and then page stuff here. Oh, I don't know what happened there. Page execute read write. What's it not like? Probably the cast. Yep. There we go. So all I've done there. Virtual alloc on its return is going to return us an address to the allocated memory. If for whatever reason it'll fail, it'll give us 0 or null value. So that would indicate to us that for whatever reason this memory can't be allocated. Just to go over what we're doing again, we're giving it the first parameters and the address that where we want to allocate memory to. We're just giving it null or 0 in this case, same thing, because we don't want it to go to a specific address. We just want somewhere it'll randomly find a free portion of memory for us in the process. The size, again, we could be that we could make that dynamic if we wanted to, but just for example purposes, we're just going to have a static 100 bytes. These are going to be these are the allocation types. So obviously we want commit and reserve memory, and then we want full permissions on the page, so we can just sort of do anything we want with it. It's not going to give us any sort of access violation. It's just the easiest to work with. But again, if we're thinking about things like anti-cheat or avoiding detection, this is very loud, so just something to be aware of. And then next we are going to want to copy over our stolen bytes. So the address of the code cave, and then we want our stolen bytes, and then it will be the size of the hook. Oh, what the blood? Sorry, I can't. Sorry, I've injured my hand. I can't type. Right, so we'll start commenting this just so creating code cave for stolen bytes. So creating the new buffer for stolen bytes here. Inserting jump in original function, and then we're going to copy over stolen bytes to newly created buffer. Happy days. And now once we've got our stolen bytes added, we're going to want to add some stuff onto the end of our stolen bytes, which is going to be a jump back to our original function. So that would be, there we go, trampoline code cave ID. We're going to want to set the plus size, and this would be the jump, so x9. So adding jump after stolen bytes, jump back to original function. Happy days. And then after this, all we're going to do is another calculation. So underscore t relative ID. So we're going to, if we remember our from J. Bremer's article, it's function b minus function a minus 5, the size of our full jump instruction and the addresses of the relevant locations that we want to go to. So we're going to go from our original function to our code cave. So there we go, code cave, and minus 5. Happy days. And then we want to insert this after our jump. So 1 byte for our jump instruction up here. Remaining 4 bytes of relative jump, and then we want that plus 1, and that will be our relative address. Happy days. So cast that in case we have any problems. I don't think there's any issues, but just in case. And that is incorrect, so we want size. Double check all this. So a relative address. Yep. Our trampoline code cave. Yes. And then obviously accounting for our jump instruction. Happy days. Once everything's set up, then we can return our address of a trampoline, can't we? Return trampoline code cave ID, and just realised we made a void, so we want to create that UN pointer. UN pointer t. There we go. Happy days. Right, so we'll just quickly go through all this function line by line just to reiterate what's going on. So right away we're just creating a buffer for the stolen bytes that we're preemptively just getting this ready for what we're going to copy from the original function. Then we're going to insert a jump in the original function from our the original function there into our custom function, and obviously that's our size of a hook that we need to calculate how many stolen bytes and sort of what we're going to be how much space we're going to need and all that there. Then we're creating our code cave over here. So this is going to be where we're going to insert the stolen bytes and then the jump back to the original function. So that's all we're doing here. I've already discussed virtual alloc. We're finally copying over the stolen bytes to the code cave, so then we can re-execute them before we jump back. After the stolen bytes, so in the order of things, if the compiler's sort of going through line by line, stolen bytes, then this will be our jump instruction here. So stolen bytes will be executed, then the CPU is going to go to the jump instruction. It's going to go jump to wherever we've placed, or whatever address is there. So what we're doing there is we're adding the jump instruction after the size, and the reason we're doing that obviously is because we've added the stolen bytes there. So we're not just going to add it at the start of the code cave, otherwise we would overwrite our stolen bytes, which is not what we want to do. And then we're going to calculate our relative address. So obviously the destination function minus the source function minus 5. So we want to go back to the original function from our code cave. So that's why these parameters are there. So it's going to be our source function minus the code cave's location, then minus 5 for the full size of the relative jump instruction. 1 byte being the jump, and then the other 4 being the address. This would change if we was obviously in x64 and things like that, but we'll cover that in the next video. Alright, so before we begin inserting a trampoline, I've just quickly recompiled this just so we can calculate our sort of relative offset again for this function. Obviously the reason why I'm not using the address from our module here is just so we don't end up in our jump table. Why is it crying? There is no main. That shouldn't be moaning at us, but it is. Happy days. Don't quite know why it's doing that, but it shouldn't do that, but nonetheless it is. Okay. It's because it's an old version. Happy days. There we go. So we'll just quickly open this up in x32 debug and just find our original function. Obviously our symbols there, so I believe it's called test func. Is it test function? Happy days. Just double check it is the correct function, and then we'll be on our way. Yep, test function is the one that we want. So we're just going to get our relative offset here, and then we'll be on our way. So that is the, there we go, yeah, it has changed. So all we're going to do now is just set up our initial trampoline. So for what I was discussing previously about our function return pointer, we're just going to use that now. We're just going to set our trampoline equals trampoline. So we're going to want to go from module base plus where we've just been. There we go. Oh, bloody hell, my typing is atrocious. Sharp pointer, and then go bang, bang. I want to go to our hooking function, don't we? And hooking function, and then the size of it will be 9. Nothing's changed there. Sharp pointer. Happy days. There is an issue because it's a type. There we go. So now all we're doing is just setting the return function pointer from our custom function here. So now, all going well, it should execute the original function, so from test func, and then it'll go into our hooking function as well, and also execute this here as well. So we should see 2 prints, one saying test function, one saying hooked, all going well. Let's quickly stop debugging here. That would be happy days. Just double check that everything is okay. Address test function, set trampoline. I can't see any problems with this just from looking at it, so we'll quickly see how we go. Oh. Our original function is not getting called because we are not actually return. We are. I bet if I go in our hook function, we are probably not. Yeah, we're not. No. So I left in the little error I made there, just obviously highlight where I went wrong, and obviously me finding it as well. So all I did there is I just wasn't actually returning the original function address as we just assigned down here. That's why it wasn't working. I'm just going to step through and sort of see how the trampoline's displayed in memory now, just so you can see it. I've also added a print instruction in here as well, just so you can clearly see it. What I'm going to do, I'm just going to quickly get rid of some of this stuff in here that we don't need. Yeah, we don't need this function, do we? Just makes it a bit clearer to see. Yeah, happy days. These are just our original function, hooking function. I've just moved these up here as well, just so we can call it from our hooking function as well, just so when this function returns, our original function to get executed as well. As we're going to see now, it might have broken our. It has indeed broken the original function. We'll quickly get that back, don't worry. Address of func, happy days. There we go, test function. Copy. Nice one. So I'll change that. Obviously, I changed a function. It's just altered where things are going to get mapped in memory. So now we've done this, we should have our. There we go. As you can see, our trampoline. As I explained there a second ago, I've just added a little print. So it displays to us where the code cave has actually been assigned. So we'll step through this now. So if we go to the code cave, we can see what's happened. So our stolen bytes are just some random portion of memory that it's assigned to us. Here's our stolen bytes that we've got, and then we've got to jump back to our original function, and it's jumped after we've executed our jump. Obviously, we're just going to go straight back to this function here. It just go in an eternal loop, and we'd never actually execute the original function. But now, obviously, we're jumping after we've inserted our padding and our original jump back to our function. It goes straight back here. So we'll step through it all in a wanna. Hooking function here. Halfway through the hooking function, it goes back to our function pointer here, which is obviously pointing to our stolen bytes, our code cave. And then once the stolen bytes have been executed, it just goes through here. We'll step through it in real time as well. So while I've got it, there we go. Oh, no, we won't. Do we even have a breakpoint on it, or is it disabled? That is why. There we go. So we'll step through it in real time just so you can see it. So we'll go step into, there we go. It's, as you can see, it's going to our hooking function here. And then if we just step through this, our hooking function, then we get down here, we will step into that as well. Here we go, going into our code cave. Once you're in our code cave, jumps back to our original function, or after where we started. Hopefully you all got something from that. In the next video, we're going to cover this in x64. So as you can see, there's not a great deal to trampolines. They're pretty simple. Occasionally I get a little bit confused just going through them, so I get confused just sometimes with the setup, but obviously they are really simple. It's just, yeah, just one of them things. When I first started learning these, it really did boggle my mind a little bit, and I'm not too sure why, because again, they're unbelievably simple. But yeah, hopefully that's a little bit more clearer for you and sort of things you can achieve with it. Next sort of set of videos, we're going to be covering some more cool things, and again, real game hacking soon. And I've got some videos planned for that, so we'll demonstrate these in the real world as well, so you can sort of see how we can use them, not just in examples. But yeah, thank you ever so much for watching. Hopefully you've got something from it.